Okay, let's get started. What I'm going to do is go over and backtrack a bit here because I got a lot of requests last week for people who wanted to know something about pointers and C as a base language. So today I'm actually going to talk about C and C++, but mostly C because C is the base language for Objective-C. Differs a bit from Java. So this lecture here is the one that's called Objective-C Overview. And it's right before the lecture one. This is the last one I haven't finished yet. I'm going to go back to that one. And this is where you're going to find that first assignment I just talked about a few minutes ago. Also, the lecture one examples are out here as well. So C and Objective-C for Java programmers. So I can teach you the entire language in probably about an hour or so, maybe longer if I don't finish today. I'm not going to rush through it. If we don't finish today, we'll finish on Wednesday because you already know another language, hopefully. If you haven't taken the Java class, don't worry about it. But if you have, I've compared everything to Java. So why learn C after Java? Well, usually people learn C before Java because C is an older language and they've been programming for a while. But if you learn Java first, which a lot of people are doing actually right now, then you forget, or it makes it harder to learn Objective-C and C++ actually. Both Objective-C and C++ are built from C. All of these are different languages. However, C is the base component of both Objective-C and C++. So they're in parallel with C underneath it. So C is non-object oriented. C is procedural. Functional, not functional, it's an imperative language actually. That's a proper category, it would be an imperative language. But there's two separate object-oriented versions of C, which is where we get the C++ and Objective-C. C++ is the Windows side of things, follows a different format. So what I want to talk about is the history actually to tell you what this NS everything is and everything, you know, what does this mean, all of this stuff, which is hopefully because you see the big picture and then you'll actually be able to follow along with this a little bit better. So on the Objective-C part of it, it's also based on C. Better control of low-level mechanisms through C. So the C functions, C structures, everything that was based out of the non-object-oriented version is inside of Objective-C. That's why we can compile with GCC, Objective-C programs. The performance is much better than Java, actually. Because Java's got that JVM that we're loading on. We don't have a JVM. We're talking directly to the operating system, which gives us more low-level mechanisms. Probably not a bad idea if you're going to get into this area to actually take a C course eventually, although you're working backwards completely. Because usually you start with C, then you learn Objective-C, and then you learn Java, or you learn a higher level. Because it's not bad, because then you have more control. You can write DLLs, you can write all sorts of different things in C that you can't do in higher level versions of it. Java hides many of the details needed for writing operating system code. C is good for system calls, which is what it was really meant for originally. Operating systems such as Unix was written in C. Supports the C language based on system calls as well. So we have the ability to talk directly to the operating system through the interface, through the C language. Java, you're not really talking to any interface. You're not really talking to any operating system with Java. You don't have that capability. Memory management responsibility. Okay, so there's pros and cons to it. To be able to talk to the operating system, the native one, and tell it what to do and run system calls and stuff like that, the side effect to all that is you're responsible for managing your own memory. Java manages memory for you, 100%. Doesn't even allow you to do anything with it. So we got a little bit of differences in terms of the philosophy of who's responsible for the memory. Explicit initialization and error detection that we get in C that we don't get. We have higher level libraries in Java, higher level libraries in C++ as well, and Objective-C. So we have a little bit, but not as much, and I'll go through that. More room for mistakes in C. Yes, the more lower level you get, the more room for mistakes and issues, because now you can use pointers, now you can use all sorts of different, alloc and malloc, and you can basically allocate, and get yourself into a memory leak or something. And I'll talk about that today as well. Goals of this tutorial is to introduce some basic C concepts to you so that you can read further details on your own. And you're probably going to want to do some research on the internet or go to the Apple developer site. warn you about common mistakes that are made for beginners in terms of the C components, and get your homework done quickly. Hopefully help you, be able to be more productive so you can write more complicated code. Alright, so we looked at Hello World for Objective-C last week, and we saw it looks very similar to this. Actually, this is the C version of it. And the examples I'm going to do, actually, we can use printf, and we can use C in Objective-C. Just like the same way you can use C in C++. You can use in C++, actually in Objective-C, you can use stdio.h, which is why if you're a C programmer, you've got it made. Because you already know about I/O, and you already know about memory, and you already know about pointers and stuff, which is what I'm trying to do for you guys today, is bring you up to speed on C. So this printf, in terms of printing something to the screen, we've got escape characters in here. We're printing out a message we're returning. In C, this was a function. In C++ and Objective-C, this would be more of a method, actually, in an object-oriented context. This particular output says hello world NU, because we have the NU here that's with a tab, a new line, and a tab. So we have the new line return and a tab where we're getting this NU from. Simple example. Looks very similar. We have in C, we have the opening and closing brackets. We have the return, even though we don't need it because this is void main. We don't actually need a return in here. And we have void in here, which we don't actually need this in here either. We could leave out the void. So in terms of the example, the include stdio is equal to the include file. Include the header file, stdio.h, which is the standard header file. This works in Objective-C, by the way. No semicolon at the end, small letters only. C is very case sensitive. If you put that in capital letters, you're going to get a problem. So it's only lowercase letters for everything in terms of the libraries. Void main is the only code executed here is inside of main. Nothing else in this program is going to be executed. This is equivalent to the main.m. or main.c in this particular case. This is the driver program that has main in it. Printf is the message you want to be printed inside, so we have printf. That's a function call. So prior to object orientation, we created functions and we ran functions. That's all we had. That's all we did. So main's a function, and we're calling a function inside of a function with printf. So we have that opening and the closing bracket, which is a different syntax for C. But it's the same concept. We're running functions. We also have functions in Objective-C. We also have these characters here, the /n for new line, /t for tab. The desert, this is here, this little line here in front of the special characters within printf. We see it here, special characters here. We don't have any special characters. Well, here it is here. The rock, we wanted to print out the quotation marks. Inside of the quotation marks, we would get an error message until we put these guys in here that separate it. Basically, it's an escape sequence that says, don't take this word for word. Hold off for a second, read what comes next, and print it out as if it were just a character. It's not a... This basically says, instead of this being a keyword or key character, it's not. It's just text. This works in Objective-C, by the way, as well. We also have simple data types. So we have in C, C++, Objective-C, all these variations of the languages here. I don't particularly like this slide because it's sort of word wrapping a little bit, but what we've got here is integers, we've got characters, floats, doubles, longs. You're going to look up essentially whatever it is you're going to use in your programs, but the basic primitive data types. This is the interesting part here, these, %C for character, %F for float. You can actually support it here with an I and not a D. This is a double actually, or LF here for long float for double. So, and long for the L. For the short, well, short's not on here, but integers could be D's. They can also be I's actually. Just the plain old I, lowercase I. Notice that these are all lowercase characters as well. What does this mean? It means what you're using inside of the printf and the scanf. And the scanf actually is the counter Yeah, it scans the input. It's kind of like the system.io.in and system.io.out in Java. So in this particular case, we've initialized a variable with int. Same thing we get in Java. Int in number of students is equal to 0. Printf, how many students does ITU have? Scanf, the number of students here, read it in from the input. Printf, ITU has blank. And this is where that D, that the $D is coming into place. Well, it's an integer. You can use the D with an integer. And this is the %. Has this number of students, and then we're printing out the number of students. So this is really a function call taking on a string. This special character here, this %, and it's all special character oriented. This is saying, substitute this parameter with this one here. And it goes in the same order. So if I had 2 of these in here, I would go n students, comma, y students or something, I don't know, whatever that second parameter was. And it would substitute from left to right in terms of the sentence. And then return. So stop me if I'm going too fast. I'm just kind of trying to make this a best of all worlds here. In C, we have something that we sort of have in Java, but this is a little bit different. In Java, we upcasted, and I remember I said it's like type checking, or type conversion, or typecasting. It really is like typecasting. So type conversion, let me talk about that for a second. We have that in C, we have that in Objective-C, we have that in C++. We don't really have this in Java, because we don't do very much of this. Instead, we upcast, downcast, and we change object types to certain levels in the hierarchy. Alright, so what do we have here? We have integer I and j, which is equal to 12. I is not initialized, only j is, because it's the second one here. This is meant to kind of just show you a couple of examples of a few things. We could do the same syntax in Java. Float f1, f2. f2 is equal to 1.2, which is a float value. And then we have this. This is the same thing we saw in Java, and we call it a cast. We said, get this person and change him into a human, or take this student and change him into a person. But in here, it's really a type conversion instead of an object conversion. So when we say integer, and what we put, the only difference between it is we put those data types in here. So we say, take f2 and change them to an integer value, because f2 is a float and I is an integer. And then make this I equal to the integer version of this. So an explicit call, so I is now 1, which was, the 0.2 is essentially lost. So when we typecast from different, we're actually working directly with the memory. We're taking what's at the memory of that identifier. And we're saying, you used to be a float, now make you an integer. We're losing the precision and we're rounding up, or we're changing the value. Caution. You can actually make some significant mathematical errors. In fact, you're not even rounding in this particular, it doesn't round in this particular case, it just cuts it off and truncates it. Different than object conversion when you can go back. Here you can't go back. You can't take F2 and go back to a float. You're going to be stuck with a float. It's going to be 1.0 is essentially your float value. So word of caution, it's not the same because of that conversion. Explicit conversion rules for mathematical operations also exist. X is equal to y plus z, converting y or z as a double, float, integer, character, short. So you typecast x's type to whatever it is you're assigning it to with the assignment operator. And that's another way of converting it. Moral, stick with explicit conversions and there's no confusion. You want to avoid typecasting because you're going to not only lose information, but you're going to confuse the reader of this code, and it's not going to be, not necessarily going to be the desired effect that you're looking for. So let's take a look at the different operators, just like C, so like Java, like C. Operators such as, same as in Java, we have the same arithmetic, same expressions actually, logical expressions are identically the same as well. Syntax is the same for if, else, while. So you practically know the language if you know Java, you already know C. So in terms of the operators and the syntax. There's another example here where we didn't have this actually in, this is a constant character actually, define danger level 5. So it's a C preprocessor substitution on appearance. Like the Java final, we don't have final in C. Instead, we have define. So we do it at the top, and we're creating a character. We're basically creating a variable that doesn't change. We can do this in ObjectiveC as well. So we say in here, float level is equal to 1, if level is larger than or equal to, well, that's the danger level, which is 5. Replaced by 5, so low on gas, good driver. I don't know. We'll just go through an if else statement essentially. Yep, you can. Yeah, anything you can use in C, you can use in ObjectiveC. Just the same way as everything you use in C, you can use in C++. C++ is just like C.
No, there is not.
Plus plus. ObjectiveC is just like C. Well, but there's no plus plus, but there's, ObjectiveC. It's the base language. C is the base language for both of those two. So just like, when you, sometimes when you're taking a C++ course, you're not really taking C++, you're taking C until you start building a class. Until you actually build an object in the language, you're using C. So you can actually write C and compile it as an ObjectiveC program and put it in an iPhone app. Until you make an object, you're not even using ObjectiveC, you're using C. So it's really exactly the same concept. One-dimensional arrays. Integer number 12. Arrays are kind of different, however. This is the base C. We have arrays that, and this is kind of the interesting thing, we can make objects and use the object-oriented version of this. If we're not using object orientation, and we're just looking at the C implementation, they're fixed in size. They're not dynamic. But ObjectiveC takes everything and makes it dynamic. So we could have growing dynamic arrays. And I'm going to get into that further down the road, but you should know that the base C language, not dynamic, everything is static. Same thing in C++ as well, they act the same way. But C++ doesn't actually have a dynamic array implementation. It has a extension library that you can add on and include that will give you that capability, but it's not part of the core language. An array is a core feature of the language, core data structure. 1 cell per student. Here we have number 12 and an index value. Sum is equal to 0 in terms of some integer numbers. And then we're doing this is the same loop that you could do in Java actually. Integer is equal to 0 while integer is less than 12. Index. Index plus plus. Go through each one of them. So number index is equal to index. So basically what we've got is, in this example, is just 2 little loops that's going through the index values. So same kind of concept as we saw in the Java course. The arrays are kind of held the same way. A little bit different in terms of strings. In fact, this is the same. This works similar, but we have a separate class for strings in C++ that don't exist actually in C. And we have a NS string in ObjectiveC, which I'm going to get to, that is interesting because it's kind of like this string, but it's based on a similar logic but on a different platform. And it's for memory usage. So here we have character name 6. So it's a character array that's implementing a string, which character arrays in C++, actually in ObjectiveC as well, character array is a string. The string is implemented in the form of a character array. So we can get at each one of the individual items the same way as we can a character array. So characters are single characters. Put all the characters together and you have a string. But in both implementations we have the null character at the end indicating the end of the string, which we don't get if we just use it as a character array, because you'd have to put that in manually if you were doing it that way. So here we have printf, and we use the $% for string in the name, so prints until printf knows that it's a string, so it will print until the null character ends up at the end. So functions to operate on strings. Same kind of functions, string copy. I'm not going to go through all of them. You can look them up. Concatenation, string character, find me a character here. Substrings, give me the string from this point to that point, from position to position. And then we have strings.h if we were working with a C environment at the program starts. So in a multi-dimensional array, we can actually have the first word, the first character, the second word, the first character, the second character. So we can go through each one of the strings word by word, character by character, and it's a 2-dimensional array, actually character array, versus a single dimensional character array. So we have the points 3 and 4. 0.34 is equal to 12, not 3 comma 4. So we print out points 3, 4, and we get a single value that shows up. It's kind of like a grid or matrix, if you think of it that way. Like Java, but somewhat like C, type conversions themselves. But you can typecast from any type to any type. In Java, you can only go from hierarchy to hierarchy. And for objects, in Objective-C and also in C, you can typecast objects, which means you can, which is why we have the ID generic object. If you know you're going to typecast, you're going to make it an ID type. It just basically says I'm an object, and then you cast it to whatever it is you want it to cast it to, and casting it basically converts it. But you have to be careful because you might lose some information. In terms of arrays, they're always initialized before they're used as well. So here we have integer number 12. Print this one here is going to give us produces undefined output, may terminate, may not even be detected, because we haven't actually populated the array. We just basically created it and printed it out. Common problem, actually, to print out the contents of an array without actually populating it. Strings are terminated by the null character as well, as we mentioned before. Memory layouts and addresses, and I'm sort of getting into the pointer concept actually. So when we create variables, and this is new stuff for Java people actually, we get in the operating system perspective the memory that's associated with the process that's running. And we have two forms of memory. We have the process space, and then we have what's called the heap space. All dynamic memory that is created after the program is created, after the program starts running. So let's say, for example, you already know what memory you're going to use in a program. And the runtime environment starts, it can allocate right there in the process space all that memory. We know we're going to have, in this case, we know we're going to have integer x, float, you know, we're going to have all this stuff here, right? So we know we can actually populate it. So we do that, and it's called static allocation. And the addressing that occurs at runtime because we don't know what addresses we're going to have. And the programmer never actually gets any addresses. We don't even know what address we're going to be running at. This is totally different from Java. Java, we don't think about memory at all. So in C++, there's two forms, excuse me, C++, Objective-C, C, and C++, all three languages. There's two forms. There's dynamic and there's static memory. C supports both. Objective-C is purely dynamic, which means each location here is allocated at runtime through the heap memory of the object space some address. It's not. It's so whether it's pre-configured or whether it's allocated at runtime doesn't really matter, except for one thing. When we allocate, we can deallocate, which is why in Objective-C we have in this alloc, and then we have release. We have all of these different terms in there to allocate some memory and then deallocate the memory, because we have full control. C++, not so good, not full control. It's half and half. It's like a hybrid. So the heap memory is used in C++ for dynamic, and then we have static, you know, load time. So we have both models actually in that. But you know, so it depends. It doesn't really matter which method you're using. You just have to be familiar with what's available to you. So as this particular example, we have what's called offsets, and we also have what's called the memory. So integers, here we have two integers. We have integer x and integer y, and they're 5 and 10. And we see the space that's allocated for an integer is small. This is why we have problems with type conversion. And then we have this number here, 12.5, which is a float. So the actual space that's allocated, and this is the memory address down here at 4308. We have this one here. But if we change this one to an integer, we're cutting it in half, because we're making it small. We're making it this size instead of this size. And we're going to lose some stuff. So if we take this and turn it back, well, this is going to be half empty. It still does take the same amount of memory, yeah. But we're going to lose it in terms of its representation, because we're going to chop the field in half and shrink it to an integer size and then put it back to a float size. And then where are we going to get that stuff from? Well, I don't know. It's going to be empty. So we lose. That's why you don't want to do any typecasting in C. because you're going to lose it. In fact, you don't want to do it. You don't really want to do very much typecasting in Objective-C either, which is why we don't do it that way. If we go Object ID, and we go, okay, we're going to cast this. And then this takes care, in the language, it takes care of this side effect for us. It's not going to truncate, it's going to leave it. If we change it to this, we're going to make it big enough so it works for everything. So we can, it's a safer cast, I should say, versus assigning it a type and using it as a different type, we run into typecasting issues. So if we have a built-in generic type ID, then we can use it for anything. We don't have to worry about truncation. We don't have to worry about, is this all going to fit in here? Or is these two guys, are they going to fit over here with this characters over here? Because character is even smaller than an integer. So that's why if it's dynamic, you might as well just make it so it's generic in terms of the concept. But anyway, the concept is we have memory that's located at addresses at different sizes for different types of variables that we're using. Pointers. These are what's called named memory locations. 5 is named X. 10, which is space number 4304, address number 4304, is named Y. And we don't have any of this in Java, by the way. You probably remember, never heard this stuff before. Pointer is going to be equal to the variable containing the address of another variable. Like, why do we want to do that? Because what we really want are generic memory locations, and we just want to keep track of those addresses, and we want to move the addresses around because we're working dynamically, and we want to be able to have the flexibility of using the memory without having to go, this is equal to this, and this one's equal to that one, and that one's equal to that one, to move the data around. In this particular case, when we go integer x is equal to 5, y is equal to 10, and I can say, well, x is equal to y plus 1, and now I got x is equal to 11. I'm copying. I'm taking a temporary memory space, I'm picking up this value, and I'm picking up this value, and I'm doing a lot of manipulation. When we use the memory address, we just go, instead of using the variables, we just go out to the memory and use what's out there. And it's easier to access, it's faster. So pointers make things run faster, dynamically. They make for a lot more flexibility in the program design. So here we have two examples. Here we have a data variable. I call them identifier variables. So some people call them data variables. So floatf, that's what you're familiar with so far in any other language. Okay, so here's where the asterisk comes into place. The asterisk is the reference and the dereference. So a reference, this is a reference. It says identify this here. This is going to be f underscore address. This is the name of the variable. I like to put, this is actually the syntax that I like to put this asterisk next to the name of the variable. Sometimes you'll see it next to the data type. You'll see float asterisk. Because people go, well, it's really a data type. No, because this name is really a floater. This is really a pointer name. So if I do this, I remember, well, you're a pointer. So here we have a pointer variable versus a regular identifier variable. Only thing difference is this asterisk. So in fact, we've seen it already in Objective-C. Heavy use of pointers. Why? Because we don't want to copy here, copy there, copy here, copy there, because we're picking up the memory location, taking that data, copying it to another one, copying it to another one, just leave it. When you put it out there, just leave it out there and just go to it and access it, which is what pointers are allowing you to do. So once you've got it loaded in a memory address, don't pick it up and load it into another memory address. In this particular case here, if we do an assignment, x is equal to y, you got to pick this up over here and put it over here. It's like, why? When you just change you put it all out, and instead of accessing it through these identifiers, you're accessing it through the memory addresses. So we're going to this, okay, let's go to 4304, let's go to 4300, let's go to 4308. So we're not moving anything around. So it makes it faster, essentially. It makes it more efficient. So we have this ampersand here that says, this is what's called, and it's universal, it's the address of operator. This is address operator. I call it the address of operator. Because in here I say, give me the address of f. So in here I've said f, and after we reference it here, We don't have to use this star anymore. This is the name of the variable. It's f address. So f address here is equal to the address of f. So ampersand is the address of operator. We'll see a couple of examples and this will make sense eventually. If I put the asterisk here, that would say follow f of f underscore address, which is kind of dangerous. That's a dereference. That means follow it, give me what it's equal to. So we have two things. We have the address of where it's pointing to, and then we have the information at the location that it's pointing to that we're working with. So in here when we said f, it said, okay, allocate me a piece of memory. Now I got 4,300. Our memory is pretty generic. It's actually the same as this previous slide. And then here we still have the same thing. Float, reference of f underscore address. Okay, here's f underscore address. Okay. And then here it can actually it can actually point to any address. So pointer variables point to addresses. They hold values of memory addresses. Because what we're really interested in doing is manipulating what's at all of these memory addresses without having to copy it all over the place. So we're accessing the variables through the memory addresses and not, into what they're valued at, as an example. So here when I say f as underscore address is equal to the address of f, well, the address of f is 4,300. So now what's being stored for this variable f underscore is 4,300. It's at memory address 4304. So 4304 over here got assigned the address of f. Address of f was 4,300. So now the value, if I said print f address to the screen, it's going to print out 4,300. If I put an asterisk over here and say follow, it's going to be equal to whatever's at f. Yeah. So it follows it to whatever's over there. I have some examples coming up. So I call it, well, this is calling it the indirection. I call it a dereference. So there's different terms that are being, reference and dereference. So they have directional and indirectional. Okay, it's the same kind of thing. References are pointers. So dereference is follow it, follow the pointer. So follow this here, make it equal to 3.2. So this was the address being held by f underscore addr. Address is 4,300. This asterisk says follow it, dereference it. So it goes over here to 4,300 and it makes it equal to 3.2. So we're just keeping track of memory addresses instead of copying stuff all over the place. It's what's referred to as by reference. For the reference is the memory address versus by copy, which is integer values and doubles and floats and all the variables that we contain aren't references. So why do we do this with objects? Because we don't want to copy the object all over the place. We just create the object, put it out in memory, reference the object space. And if we reference it, then it's easier to get to. We know where it's at. It's right here. So it's almost like, you create all these things, you put it out there, and then you start manipulating it. Make this guy do this, make this guy do this, make this guy do this. And so the memory, there's less swapping around and moving all over the place in memory, which makes the program run faster. Makes it run a lot faster, actually, which is why pointers are used in a lot of cases. Also, pointers could be used for passing arguments to methods and passing information to functions and things, because you're passing the whole object without actually passing the object. You're not making a copy of the object. You're just saying, it's over here. It's almost like if you had to, every time you went somewhere, you had to, pack up your house and move it to another location, and then pack it all up, move it back to another location. That's a lot of work, moving all over the place. And isn't it be nice just to live one place for your entire life? Less work. You don't have to, keep packing and unpacking, which is what objects have to do when they move around all over the place. So. All right, here we have float g, which is equal to the address of f underscore address, which is the indirectional g is now equal to 3.2. Because if we followed f, we're going to get 3.2, which is at this location, because f underscore address is pointing to 4,300. Now f is equal to 1.3. F is equal to 1.3. So f here is a regular old variable. Now he's equal to 1.3. So f underscore address is, if you followed it, is also equal to 1.3. So now we have that side effect where we have a reference pointer that's pointing to an object, and the object changes. Well, it changes for everybody because it changed at the memory address, which is another reason why pointers are good. Because one effect here affects everybody. We don't have to go back and update you every time we go to a different function or a different method. The object is changed for good. It's almost like you don't have to keep signing in because you already know that you're here, kind of thing. So it kind of makes things a little faster also in terms of sharing information. So here's a pointer example going back to C, where we have integer j and integer pointer variable, PTR. People like to use PTR in examples for some reason because they stand for pointer. So PTR is equal to the address of j. So now the pointer is pointing to that piece of memory right there. And then initialize pointer before using it. Okay, so it's equal to this address. Follow PTR, have it equal to 4. Does not initialize PTR, actually. It just follows it. PTR does not... If I said this line of code without this line of code, PTR is not initialized to anything. It's garbage. So if I followed PTR, I'd get some odd memory address, probably. This is initializing it. It's the same way as if you said integer I, print I. Oh, and there's nothing at I. So it's the same concept. So you follow PTR, have it equal to 4. Now j is equal to 4. J equals, well, follow PTR. So 4. Well, follow PTR. Well, PTR is equal to 4. So j is now equal to 4. So it's basically they're both equal to the same value. It's the same value. It's the number 4. So. Dynamic memory allocation. This is what, okay, so references, dereferences, and pointers are all dynamic memory allocation in C that translate over identically to Objective-C. This is what you're programming with. When you see that asterisk, this is what you're doing. It comes from C. So explicit allocation and deallocation. So here we have integer pointer. We allocated space to hold an integer because this is the data type. And this is the name of the data. Well, this is not the name of the data. Yeah, it is the name of the reference to the data that we've created. So in Java, we did this automatically by saying person, my person. And I said, well, that's a reference type. It was automatically a reference type in Java. Because although we don't have pointers, everything is dynamic in terms of those references. We didn't have to use pointers. This is equivalent to the same thing, except for now we're saying make it a reference. What are reference types? Well, they're variables that represent data or objects that we're creating. So we're explicitly in Objective-C saying that this is a reference type instead of just taking for granted that, oh yeah, it's going to be a reference type, because we don't have pointers in Java, because we don't have to allocate and deallocate because the runtime environment does it for us. So that's one of the luxuries we had. Here's where this alloc, malloc, and everything comes into place. Well, malloc changed to alloc. Same syntax actually is used. So we have PTR is equal to malloc size of integer. Well, we have to get the size. We have to know how much memory to actually allocate. Malloc is allocation of the memory. So we have another word for it that was implemented in C++. That was the word new. New, which is the same word we use in Java. So we say, my person is equal to new person. That's equivalent to these two statements here. Instead we said integer pointer PTR malloc size of integer. Okay, so it's a little different in terms of the syntax. The concept is identical. We're allocating space that's going to hold the size of an integer. And do stuff with the space. Well, follow PTR have is equal to 4. And then we have free, which is release. Actually, we have delete, the keyword delete in C++. Free, we actually have free. We have release, free, dealloc. There's a couple of different things, and I'll show you the terminology for that when we start looking at it in Objective-C. It just deallocates. It releases, frees up, I think release is probably the or retain. What does retain do? The opposite of release. Keep it.
That means we are going to a pointer address.
Yep.
We are giving that address as an integer size.
Yep.
And then we are giving a value into that address. And,
And then we're getting rid of it. We're deleting it.
so that code will be in that pointer itself.
After this particular line of code, there's no more for. It's gone. Yeah. What does that do? Well, it frees up. The word free is used in C++ or dealloc. There's alloc and malloc and dealloc. I can't say that word. Anyway, long story short, it makes it so that, and this is called a memory leak actually, if you allocate, and don't deallocate, don't free anything, you're eventually going to run out of memory. Because there's no garbage collector that goes around and says, oh, you allocated, but you're no longer using it anymore. We'll clean it up for you. That's what you get in Java. So here you have to say, well, I'm not using it anymore. Makes it available, puts it back into the available memory pool, makes it available for somebody else to use in the program, for your program data. Next time you go alloc or malloc, depending upon what language you're in, it can use that space. It's marked as free. So it basically marks the space as being used or not being used. So it makes it available. So you're doing your own, and then when you do retain, and that's an Objective-C. What if you're going to get rid of the pointer, but you want to retain the memory? You don't want it to be deleted or unreferenced anymore, because you're going to use it again or something. Well, then you can retain. So, reference counter. Now going back to, did I show you this? No. If you're in the iPhone class, I showed you this already. In automatic reference counting, we get this with iPhone app development. We also get this with Xcode and Coca app development in Objective-C. There's a little button down there that says automatic reference counting. Automatic reference counting means keep track of all the memory that's still being used. And then you can decrement and increment the counter when stuff goes out of scope and is no longer being used. It's not garbage collection. It's just keeping track of what memory is garbage, what memory is not being, and what is being used in terms of the number of references that are out there. That's what that feature is about. It has to do with the memory allocation. So I'm going to show you more pointer stuff, but that's the concept. But I'd like to show you the examples in Objective-C instead of C. So I'm going to kind of stop with the pointer stuff at this point. Also, after a while, it gets a little overwhelming. We still have file I/O. File I/O is the same thing. Elementary file I/O is the same thing in Objective-C. Actually, we have the file pointer. Anything, in fact, we have object pointers, file pointers, device pointers. Everything's a pointer. Because we're not going to open up the entire CD-ROM drive and copy to a memory address. Nope. Instead, we're going to go, where is this thing located? Point to it. Where's the file on the disk? Point to it. Put it in a buffer space for buffered I/O, which is normally done these days. Point to the buffer. It's in memory. Don't keep copying that all over the place because it's too memory intensive. So we have what's called a file handler, or handles. I call it a handler. Some people call it handles. File is the name of the data type that we're doing here, and it is a reference to an input file, which is going to be equal to null. So we can set pointers equal to null, which is essentially saying it's not pointing to anything, versus a pointer that's not set to null, which is supposed to be pointing to something that's being used in the program, theoretically, hopefully. So open a file for writing. We use the W here for writing. Reading is the R. String them together for read, write, and whatever. Open, read, write. We're just going to do a check here. We're going to run an exit one. Needed to explicitly error check it. There's no automatic error checking. Actually, the exception handling in Objective-C is not the same as Java either. There's no automatic built-in APIs for it. You actually sort of have to do your own checks and stuff. But I'll get into that in a few minutes. Just like print, F prints for file printing, also supported on the input file. So this is going to open up a file for writing, put hello world in the file, and then close the file. Which is what we're doing here. So don't forget to close the file. This is just an elementary example on how to do file handling. Error handling. The moral from example. Unlike Java, there's no explicit exceptions, which is the same for Objective-C. Need to manually check for errors. No exception handling. You can't throw exceptions. They don't exist, which is kind of okay. Whenever you're using a function you've not written, you're going to actually have to check, make sure it's okay. Anywhere else errors might occur, so you have to do your own checking. So functions, why and how, to get into the function concept. If a program is too long, make a function out of it, and then you call the functions and so functions and methods exist in Objective-C. Because Objective-C is part of C, we have functions in C. Methods are just functions inside of classes or that belong to classes. And we can run a function in association with a class, and we can run it outside of the class just as a function. So that's where we get the class functions from. You just run the function. Belongs to the class as an example, but it's just a function that we're going to run on the class because we're working with that class or that object. Versus methods that are associated with the object, which are those instance messages or methods that are associated with the object behavior. So in some contexts they're behavior, other contexts though they're just functions. So if the program is too long, we can create a function, just run the function, call the function. Sometimes repeat code. Modularization is easier to code debug, code reuse, just copy and paste the same function. Passing arguments to the function, we can do pass by value or pass by reference because we have pointers. In Java, everything's passed by reference actually, which is kind of weird. In C++, we have both. Objective-C, we have both because we have both in C, which is where this is coming from. Because functions are C. The method is whichever language you actually put it in. Return values from function can be both. We can return a pointer or we can return a value from a function or a method actually in Objective-C. So the basic example of a function here, we have sum. Sum is going to take integer A and integer B and add it together. And so we have that function prototype. This is where that function prototype concept comes from, which we don't have in, well, I shouldn't say that. We had function prototypes. They were interfaces. In Java, we put them in an interface. In Objective-C, we put them in a header, well, .h file, which becomes the specification, or the, what do they call it? Now I have to go between languages. The interface file. So it's still called an interface, but in C++ they call it a specification and an implementation. Objective-C they call it an interface and an implementation. So. And in Java they call it an interface and a class. It's the same concept all over again. It's the function prototype if you're in C. So here we have main and we have integer total is equal to, well, we're calling the function. We see a lot of this in Objective-C because we're actually running functions. And even in the like hello world can actually run a function. If you wanted to print something to the screen, you just run the function. So. In Java, if you did this, people are like, well, you didn't make an instance of a class. How can you run a function? Because we don't have functions. We just have methods. Printf here, just print. This is a function call as well, actually. Printf is a function call. Yeah. Here's the function declaration down here. There's the function itself. In the old days, they used to put these in the .h files and they include the function declarations. I don't know why. Well, if you had a lot of functions and were reusing them all over again, why rewrite it? Instead, just put it in a header file and include it. Because including basically just said include all this stuff. In Objective-C, you can include and you can also import. You can do both. So you can use that same concept if you wanted to. Arguments by reference. So if we do this here, we have integer sum. So in the previous example, this was by value because we're not using pointers up here. If we go by reference, we're passed by reference versus passed by value. We're passing here now the reference, which is the memory address, or the pointer variable, not the variable. So this doesn't make any copies. This takes a copy of A and a copy of B, and it uses it inside the function. It returns A plus B, which is the return value. A and B never get changed. They just, because a copy of them is used, which is why they call it pass by copy. In the reference example, PA and PB, pointer A and pointer B, they're going to be changed. So when you do a reference, You're sending, this is the same functionality, same program as on the previous slide, except for these are references. So what ends up happening is whatever's at the memory address of P and whatever's at the memory address is going to be changed permanently. Which might not be a good thing, but you're doing it by reference because you want it to change. So if you didn't want that, take out the pointer and just send A and B to it and you send a copy. So in here we have the call to the function. The call to the function is going to basically take the arguments and they're going to be passed by reference. Stop me if you don't have if you have questions between pass by reference and pass by value and these things. Why pointer arguments? Because it can get kind of heavy making copies of all this data. Plus, what if the purpose is to manipulate the object, to swap the memory, to do something with it? Then you got to end the function. You know, in the old days, you know, you thought about functions and you went, well, I want to pass some information to the function. I want A and B to be added together, and I just want it as a return value. And then we got smart with objects and said, well, what if, you know, why do we have to copy it back into the object once we return it? Why don't we just send the object, then the object can change, and then we don't have to return anything. So there's no return value that actually has to be copied to so another value to another value. There's not as much data swapping going around. Makes it faster. So when you want to change the argument itself permanently, you just pass by value. So here we have integer swap, void swap that's taking on two integers. This is the function prototype. Down here we have, we're going to pass by value. Number 1 and number 2, so what does it stand for here? And then we have temp is equal to n1, n1 is equal to n2, n2 is equal to temp. Okay, and now we're going to print out the numbers out here. Well, we're going to get a different value than if we took the pointers in here and we printed out. Well, then we're going to get the changed values because we're not returning anything. It's a void function. We're not returning anything. So out here it's going to give us the changed values. This is more popular, especially working with object orientation, because we want the objects to change. When we manipulate the value of a data piece of memory in the object, let it change. This happened for us automatically in Java. In C++, actually C++ also Objective-C, we have to tell it explicitly pass it by reference, which means use the object, change the object, don't protect it. So in Java we had, actually C++ too, we had this keyword constant. We actually have the same thing here. We can make it so it doesn't change. We can pass a reference and treat it like a value. But why do that when you can just pass it by value? Don't pass it by a reference and you don't have to worry about it. It's just a value because it's not going to change. What's wrong with this? Well, we're going to do something. We're going to pass it a pointer. Will this work? P. Follow P. Well, what's P? P is going to be sent. Oh, it's a value of P, the memory address. So it's a pointer value, but we didn't send it. It's not going to work. Because we're working with a memory address, and we sent the memory address to something else. And now we're saying print it out, follow P. Well, we didn't actually follow P when we sent it. So pass to return the reference. Compiles correctly, but it's going to give us a runtime error because the code here, there's no syntax error with the code. But we probably should have put an asterisk up here. Follow P and send that to because, you know, it's going to be equal to the address of temp, and temp is going to be, you know, even so, it was expecting a reference, and we sent it a value. Long story short, this is what happens, and this is what makes Objective-C and C actually more complicated than Java. Because you have to worry, well, what is that method doing? What does it take? And then you send it a reference instead of a value, or you send it a value, and then all of a sudden it works, but the program doesn't work right. You know, you get all these weird results that come out of it. So, but it works. So that doesn't work too well. Passing and returning arrays, and I think maybe I'll have maybe the second assignment we'll do with pointers, perhaps. Now that I'm thinking about this, might be a fun experiment because then I can go over half of it in class and we can see how it works. Passing and returning arrays. Arrays are funny and they're an exception. The same thing happens in Objective-C as happens in C. They have this funny side effect. Arrays are always treated by reference even though they're by value. So if you send an array to a function, you change the array. So here we sent the array, integer array with integer size, and integer list here. We're going to create the array list. We're sending it list, comma 5. We've sent the array, the entire array, and the size of the array to the function. It's always passed by reference when we send in the array, even though we're not using pointers. And you probably just said a few minutes ago, well, I'm going to memorize this. Easy. Easy. If it's using that little asterisk thing, they're talking about a reference, and if I don't see the asterisk thing, then it's passed by value, not reference. And then you meet arrays and you go, well, the exception to the rule. So arrays is passed by, you're doing a pass by value, but it's being treated like a reference. Because arrays are one of those funny objects that were implemented in the language as a reference, but you don't have to use a pointer with it. If they had just required you to use a pointer with it, that would solve a lot of problems over the years of understanding. But the pointer makes absolutely no sense because you can't have a reference to a reference. Actually, in C, you can have a reference to a reference to a reference to a reference. And many references, that's when you see the string of asterisks in front of it. That's just insane. That's just overly complicated is what that is. All right. Here's the memory layout of a program, and this is what I was trying to tell you about here with the heap and the code and the stack. I usually write this the opposite. I usually turn this upside down because I like to. If you took my operating systems course, I did it. Did you do that? Is that why you're smiling? No. Okay. All of the
Every time we say you do
opposite upside down. I think of the world upside down. Oh, that's why. Yeah, you're right. I think of things upside down commonly. So, because here's the thing. So, like this is known. So if I were actually going to build this, in fact, this is upside down because the zero's up here. I put the 0 down here and go up to 12,000 because this all is known, right? And who starts at the top of a memory location? All right, if I flip it around and look at it, or you can look at it this way, the heap and the stack grow into each other. In C, in Objective-C and C++, this is the runtime. Not the same as Java. Java has a different runtime and spec. This runtime spec is nothing more than the process space, because everything runs in a process. It goes from 0 to some maximum offset of memory locations. The stack are all the instructions. That's the local memory function calls. All sorts of things end up on the stack. So if you write a recursive function in C or in Objective-C for that matter, adds to the stack. Adds to the stack, adds. A recursive function is a function that calls itself again, but until it's returned, it's not removed from the stack. You get common errors called stack overflow errors, and you can actually get these with Objective-C as well, because you can fill up the stack. It's compiled with GCC. It's the same as C, essentially, in terms of that problem. Can also get out-of-memory errors. That's when you allocate. You only get this amount of room for the data, which is the heap, and it's called dynamic memory because it's being allocated at runtime. All of the allocs end up here. All the normal variables end up down here. This you can play with. This is another reason why people like pointers. Pointers go up here. When you allocate pointer space, you could fill this up. They're both growing into each other. Which means if you don't have any data, you can have all this space. Otherwise, you can only have up until the stack. And what ends up happening is that there's no warning that says, hey, you're running out of memory. Hey, you're running out of memory. There's no garbage collector that comes in here automatically like Java and picks up all the, okay, let's make this available. Let's make that available. Let's reuse this. Let's reuse that. Instead, what ends up happening is this keeps growing and growing and growing and through all the allocs, and you haven't freed anything. Your program's going to crash eventually. Bottom line, because you're going to run out of memory. You usually end up with memory overflow errors, or you get memory out of memory errors. Something memory related means you've allocated too much without deallocating. Okay, so we have multiple programs with multiple files moving right along here. We have include this one, include this one. We know about the opening and closing brackets. We know about, hopefully, for this says the current library and the current path directory. This says in the current directory with the same syntax actually for Objective-C. Run this program. Okay, out here we have the other file. So we have homework.c, we have myprogram.c, we have myprogram.h, which has the piece of data in here. See, those are called library headers. We have standard and user-defined headers. Same thing that we have with the implementation and the, I was going to say specification, but the interface files that we have in Objective-C. We also have externs. So the keyword extern, character user to line 20. Global variables defined in another file, they're external, which is all that means. It means it's not here, it's somewhere else. So global for this file, in terms of this file face, which means let's make character user line 20 okay out here. It opens up the scope, which means they're determined external. It could be in a separate include file, they could be in the current file. If they're included, they're in the current file, essentially. But long story short, it's a global variable. It's being used inside of the scope has now changed, it's being used inside of a method, being used inside of a function, anything that's associated with the program, it makes it a global variable. It's external. So you can use it anywhere you want. We don't have those in Java. So we have those. We don't have structures in Java either. A structure is just like a class. It's held multiple different data types, and we actually have unions in C as well. I don't know if we have unions in Objective-C. I have to go look that one up. I haven't used structures and unions in years because everything's object-oriented these days. But this is the non-object-oriented implementation of a similar concept.
So we don't use structures.
We can use. We could. You can use a structure, or I believe a union should be supported. Actually, I believe that both of them should be supported.
It's not necessary.
Not necessary at all, but if you don't want to create an object, you can create a structure. People create structures because they want to keep track of an integer, a float, and a double. Or they want to keep track of 3 integers, and they want to keep track of multiple pieces of data and put them all under the same name. So, here's an example, birth date, month, day, year, or date, month, day, year, of any date. So, just like a class looks like a class. The only difference is that it usually just holds data. Believe it or not, though, you can actually put member functions inside of a structure. Don't know why you'd want to do it seriously, but you can. And a union is just a structure that only has one value at a time. So it only supports one value. So why do it? Well, because polymorphism. So if you have a weight, is it a weight in tons? Is it a weight in ounces? You know, it depends on what piece of weight data you want to represent. So for polymorphic reasons, you can use a union. Structure, why not just make a class? So, but some people don't want to do it. Lightweight class is that structure kind of thing. So there's no new needed, you just use it. So we have structure, birth date, my birth date. So new, it's just like Java. The new is actually just like Java, but there's no new needed. And then basically it's kind of like the Java data type. Birth date dot day is equal to 1. You use the dot notation with it. And then basically just like a class, except for it's not. So here's another structure example of a person. Person's got a bunch of stuff in there. And then we have a structure inside of a structure. So we embedded a structure in there. And the structure is the month, day, and the year for the birthday. And we called it birth. So we put the name at the end. Huh? Yeah. Yeah. You can put multiple. You can go structure inside of a structure inside of a structure inside of a structure if you want. Highly confusing, but you can do it. Don't know why you'd want to do it, seriously. You can do the same thing in Java. You can put a class inside of a class inside of a class. It's like our dinosaur class that had dinosaurs inside of it. The baby class. Subclass. Anyway, so here we have me, which is person, me, birth date, year. 1977? No. Anyway, so you get the point.
In the dinosaur we used a super to get the. But here we are.
Oh no, it's different. Yeah. You can't. There's no constructors in here. This is not an object. This is just a complex data type. This is storing a lot of information. It's all kind of related, and you notice it's all data. Normally, that's what you would use a structure for. If you're going to put methods in here, create a class out of it. Don't use a structure. But you could put methods. Well, they're not really methods, they're functions. So you can run a function inside of a structure if you wanted to. But why? Just put the function outside. or create an object out of this if you're really going to go that far with it. But you have to remember, see, C++ was developed to C was developed to a certain point, and then they started going overboard on it, and then they came out with object orientation after C. So then, like, structures was kind of like the tail end, and then they went, wait a minute, no, let's just turn that, because this is the predecessor to the object, to the class. And it supports the same thing as a class, except for it doesn't support object orientation. You can't subclass a structure from a structure. You can nest inside, but you can't inherit one structure from it, and there's no interface to it either. So, it has its limitations, but it's just definitely a C concept has never existed in Java. Oh, there's no need for a structure in Java. There's really no need for a structure in Objective-C or C++ either, for that matter. But it is supported. And you'll see it in examples all the time. Passing and returning a structure. So it can be sent to arguments as parameters, to function arguments, as function arguments, excuse me, parameters. So passing a structure by a value, we have structure birth date, my birth date in here. By reference, well, we just used that reference, the pointer in front of it, and all of a sudden we want gone from value to reference. And then here, by value, we're returning it from a structure by value. You can actually return it by value, return it by reference, send it by value, send it by reference, which is the same thing you can essentially do with anything. We don't have enumerations in Java either. But this is a total C, G and UC thing. Enumerations, well, instead of saying 1 is equal to this, 2 is equal to this, and 3 is equal to this, we're putting a name on it. Month is January, February, and March. You know, January is 1, February is 2, March is 3. Yeah, got that right. So who's going to keep track of, well, now we all know, you know, what's the 5th month, you know. What is it, May? Yeah, I don't know. I know this is 7th, this is July. But that's a lot of memory, you know, that's a lot of wasted brain cells keeping track of which numbers are associated with which months. So enumerations remove all that problem. Now I can say January, February, March, April, May. So have the month equal to January. Oh, that's 1. So these all break down to integer values, by the way. So January is the same as the month dot January in terms of this enumerations month. So January is equal to 1, like defining January is equal to 1. So enumerations, you probably won't use them because they're being phased out, but you might see them occasionally. You can do enumerations for anything really. Colors. You know, if you had, like, you know, select a color and it was from a color wheel and you had 255 colors or something, are you going to remember whichever one of them are? Probably not. Instead, you're going to have red, blue, yellow, and then that translates in all those numbers that are out there in terms of the RGB codes, which is what a great enumeration. That's actually an enumeration that's built into practically every programming language. Well, HTML, it's built. When you say, you know, font colors equal to blue, it's just an enumeration, which is the concept. You're taking blue, and that's some shade of royal blue that's defined by the RGB code that's embedded in the enumeration in the language that's defined. And then you can come up with your own numbers and enumerate them to your own colors if you want. Same concept. We also have synonyms for data types, which are the type-defined integer employees. All right, that means rename integer to employees. Well, actually, it's not really a rename. It's type-defined. You're defining a new type, which means integer is still around, but so is employees, and employees means integer. It's like the same name, which is kind of confusing. We don't have type defines in Java either. Easier to remember, cleaner code. Yeah. Person PTR, same as the structure person PTR. So we have type defined structure person as the pointer PTR. So you're not using the pointers anymore, actually. You can take the pointer out. So they come in handy for making things cleaner looking, to the most part. So more pointers. So we have the integer month 12. The month is a pointer to the base address 430. So the name of the array is the base address, the starting address, because arrays are pointers in terms of their implementation. So when we say month 3, we're taking the address plus an offset of 3. and we're timesing by, this is integer offset elements. So then we have this one here, plus 3 times 4 is now equal to 7, because that was what was at that memory address. And then we have a PTR is equal to month plus 2. So we can actually take this guy and plus and minus integer values to him and print out instead of using the index values, which is also kind of confusing as well. We can do that in C. We can't do that in Java, but we can do that in C because we have direct access to the memory in C. Well, we don't have that in Java. So we can say month plus 2. That would give us an error message in Java. Because it was, what index value do you want? Because it doesn't know where month is. But month is holding a memory address. So we can actually play around with that a little bit more. We have a little more flexibility. So the pointer address plus 5 elements in this particular case. It's the address 434 plus 5 times 4, which is now 12. So kind of like pointer math there. Two-dimensional arrays are actually stored sequentially, one right after the other. So 0, 0, and then we have 0, 1, 1, 0. There's an actual sequence to it. So we can do the same thing we did with the pointers by using the offsets and actually look at the memory addresses and work with the name of the array and kind of increment it. So weekends 2, 1 is the same as weekend. Follow weekends plus 2 times 2 plus 1. Not follow weekends plus 2 times 2 plus 1. This is an int. So it's different actually for integers versus characters versus the different data types. Because remember, all the different data types are stored differently in memory. They're not all generic like they are in Java. So arguments and argument value parameters. We see this a lot actually in Objective-C as well. This is that main. So remember we saw main before, it was empty or had the word void in there. It meant don't take on any command line arguments. But the default of the program is this like number of integer values that we're taking in here. And then we have a character, and this is, you've been working with pointers whether you've known it or not, as if you've been working with command line arguments. So here we have integer center, and center is equal to 0. Center is less than the argument value, and the argument value is how many arguments did you actually receive on the command line. Center is equal to center plus 1. Increment it, so you can just go center plus plus, also works. Printf, the argument, this value is this value center, and then we put center as the value in terms, because this is an array, in terms of the argument value. Argument values are the command line parameters. You know, when you type in the name of the program, space 1, comma, or space 2, or whatever you're typing in, pulls it up, puts it into a character array for you automatically. So this is the character. This is why you're putting this in here. If you leave this out, you can't take in command line parameters. Usually for DOS programs, you're going to need that for that, if you're going to take in command line parameters. So strings. So here we have character message 10 in terms of an array of 10 characters, which we're going to treat as a string. Character pointer P, point to a character, a single character. Message 2 is going to be equal to, this is a different way of doing it, as well as associating hello, the string, to this character array, message 2. So now message 2 is equal to all of these characters, still stored as a character array. And then this guy up here, message, is going to be equal to bonjour, which is an error. The message has a constant address to it because it's an array of 10 characters. Or P is equal to bonjour. Well, the address of bonjour goes into P because it's the memory address versus a regular old non-memory address, but it's a character array. So it's an array, which is a reference. So there's oddities in terms of how you're dealing and assigning characters and strings to arrays, character arrays. But you can't change it, so you can't change here because you're going to have messages equal to P. You're going to have an error, has a constant address associated with it. So arrays, although they're pointers and they have pointer side effects, they really aren't pointers. You can't use them in exchange for pointers the same way that you use pointers. But you can do some things with them, so that makes them odd. I mean, you can use the memory address and offset it, but you can't ever change the memory address. It's a constant variable. It's like when you said integer I, you can't move I. I is stuck. You can't change where I is located. That memory address is permanent. It's constant. But if I said integer asterisk I, well, I can point to any memory address it wants to. So it's more flexible. Let's see. Pointers to functions. So we have a function that returns an integer. So we all know that and this is the same thing for methods, actually, and the same thing in Objective-C. The data type of the method specifies its return type. Same thing in Java, actually, as well. So integer function returns an integer. Integer pointer function returns, the function returns a pointer to an integer. So this is going to return a pointer. And then we have inside here the pointer to the function argument, the pointer to a function returning an integer. So this is a pointer to a function, which is in the side of the function prototype. So it can point to functions, essentially, that return integers. Here's a pointer to a function returning a pointer to an integer. So we have the pointer, double pointer. Pointer to a function returning. So we can stack them up. Advantage, more flexibility, also more confusing. Very confusing. Here's a pointer to a function example where we have here a pointer to f, which is the function, well, where's the function here? Pointer parameter. Call function pointer f with parameter, this parameter. You're probably never going to do this, actually. Nobody likes to point to functions. Why? It's just, it can get well, it's actually more efficient, however. You're putting the function, you're pointing to the function, but you're not calling the function. Well, you're calling the function, but you're using the function in memory address instead of using the function. Like a call, you're making a copy of it. This basically puts it on the heap instead of on the stack. When you call the function with a pointer, you're not filling up the stack space. You're putting it on the heap because you're calling it with a pointer reference. So you're making a reference allocation to it instead of a stack allocation. What does it do? It makes it more efficient, makes it more flexible. Makes the function call more flexible as well. So makes it more dynamic. Doing more complicated things. Well, we got here to declare an array of n pointers. Ooh. Put pointers inside of it to functions returning pointers, to functions returning pointers to characters. And not going to bother even going through this, but this is the line of code here. You can, that's why I said, you see some of these code examples and it has pointer, 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 like a string of 5 pointers. And you're like, why? Just break it all out. It makes it a little easier to read. Build up the declaration up in stages using type defines. Let's add type defines. I don't like type defines either because it can make a pointer look like a non-pointer, and then you're working with it, you don't forget what the type define was originally. Oh, this is a pointer. It makes sense to say Boolean, you know, especially when the language doesn't support the word Boolean, and Boolean is going to be a 1 or a 0, but it's really an integer. But is it really a Boolean? No, it's a 1 or a 0. I mean, it's an integer value. You're not storing true or false in there, but you're calling it Boolean. So, because the Boolean doesn't exist. So before we go into Objective-C, which is what I'm going to start next here, some things to remember from C, and that was your basic whirlwind tour through C, as it's supported only from a Java perspective, as it's supported in Objective-C. Always initialize everything before using it, especially pointers. It's just the same thing you have to do. Don't use pointers after freeing them. Happens all the time, actually. Not such a good thing. Don't return a function's local variables by reference. Not such a good thing either. No exceptions. So check errors everywhere. And an array is also a pointer, but its value is immutable. You can't change the value of that through a pointer. So let's talk about Objective-C and how that differs from C. So it's an object-oriented language. It's an object-oriented version of C. It follows ANSI C-style coding with methods and small talk. It's a variation, actually. It has C. The object-oriented part of it follows the small talk line of thinking, which is why it's different from C++. C++ doesn't follow small talk. C++ is actually sort of unique in itself in terms of what it follows. It's kind of more rigid. You might think that C++ is more original in terms of its design. C++ is a combination, Smalltalk and C. So there's no formal written standard. It was never standardized, which is interesting. And Smalltalk, there was like 3 or 4 different versions of it. There was the Xerox version of it, the IBM version of it. Smalltalk is not a standard language either. You base a language off of a non-standard language, you're going to get a non-standard language. Relies mostly on libraries written by others, not by the makers of Objective-C. We'll talk about that in a few minutes. Flexible, almost everything is done at runtime. Everything is dynamic. So you don't have to remember everything's dynamic. Dynamic binding, dynamic typing, dynamic linking, everything is dynamic. So Objective-C was invented by 2 men, Brad Cox and Tom Love. Brad Cox he's actually still around. I don't know about Tom Love though, but this guy's actually done a lot of books too. He's the one to buy a book from because he's like the godfather of it. So one of the inventors. Both were introduced to Smalltalk at ITT in 1981, so it's not that old of a language actually. Cox thought something like Smalltalk would be very easy in application developers. Smalltalk was a very proprietary kind of system that worked on, embedded systems. In fact, think about it. It came from Xerox and IBM. What were they making back then? Printers. Actually, Java started out as a printer language as well. The operating system you're going to put on a printer if you're a Xerox. And then your Xerox park, and you start making, well, this is a nice language. Let's turn it into a programming language. And then you get a printer language that turns into a programming language. Okay. Worked on the very simple. And then originally the Xerox part of it, this is the slides giving you the Objective-C portion of it. I think I have another slide here that's got some of the Xerox Park, like Adele Goldberg was one of them actually that worked with Smalltalk, and I think I gave you this story already. It was like to teach children how to program with building blocks. And the building blocks were the objects, and you put the objects together. So the language itself was actually designed for kids. Think about it. It's supposed to be the easiest object-oriented language out there. If you ever get an opportunity, it's still around, still supported, to look at Smalltalk, you'll go, oh my god, this is the most confusing language I've ever seen. Because it follows model view controller to the to the spec. You can't program it with it without using a model view controller perspective. But once you look at Objective-C for a while and then you try Smalltalk, easy. Because you're sort of learning it backwards. Because you're learning Smalltalk through Objective-C. Because it's very Smalltalk-like. So Cox thought, so Cox modified a C compiler. This is how it actually ended up with C. You modify the C compiler, because you don't want to write your own compiler. You modify the compiler so it works with an object-oriented extension of C. Then you call it and it actually was called object-oriented PC. So then it turned into PC from final project to Objective-C. So Tom Love actually acquired a commercial copy of Smalltalk 80, bought it basically, while working at I can't say that word, Schlumberger Research, I don't know. So with direct access to Smalltalk, because he owned it, which means he got the documentation, you could just buy the language. Well, Smalltalk 80 was purchasable, I guess. It wasn't really widely used, actually. This was before Java, by the way, as well. Java came out right after Smalltalk. So he added more to the OOPC, making the final product Objective-C. In 1996, they released Objective-C through the company called Stepstone, which no longer exists. And then Xerox PARC actually went to, Park Place went to Digitalk, that went to ObjectShare, that went to something else, and it's still in existence. So, and they're still making, this is where the NS is going to come into place as well. Here's why everything is called NS. So, Next Step, which came from Stepstone, because that was the name of the company. So their company in 1986, they released the first version of Objective-C through a company called Stepstone. 1988, Steve Jobs purchased Objective-C license from Next. Well, Next and Next Step, which were two kind of concepts. This is the NS stands for the next step. NS this, NS that. It was like trivia night. So we used Objective-C to build next step operating system. So Objective-C actually was an operating system before it was a programming language as well. Well, it came from an operating, it came from Smalltalk, which was an operating system for printers. Or actually started out into, and Java was an operating system for printers, so all of them came from, and C was an operating system. There is an operating system, Unix. So long story short, it was very operating system intense. Objective-C was built from Next Step. Objective-C made interface designs for Next Step much easier because it was working with the GUI and the interface designer for it. Next Step was derived from BSD Unix. Now everybody knows why BSD Unix is using OS X and why Objective-C. Well, it's owned by Steve Jobs. Of course he's going to use it. It's an operating system. OS X is actually based off of this as well still. So, and this is version 2.0 on OS X that we came out of. It's a highly upgraded version of it in the year 2000. Before we had a previous, still Objective-C, but a primitive kind of version of it. So 1995, Next gets full rights of Objective-C from Stepstone. So it separates out of Stepstone, becomes part of Next Step, and is licensed, well, so developed in 1993 by Next and Sun. So Sun continues, and this is actually kind of like where at one point Java started coming out of this, because Sun was part of the development of this effort to bring Smalltalk into Objective-C, which sort of like how everything came out. So One Step API, so an effort to make One Step like Objective-C, which was the operating system, by the way, implementation available to other platforms, so it was hardware. Sun is a server system. We wanted to make it IBM compatible, or not IBM compatible, but PowerPC compatible, or other hardware systems. So in order to be an OS independent, remove dependencies on the mock kernel, which was the BSD stuff. We actually put it back. It's on a mock kernel now. Made low-level data access to classes, paved the way for OS X and the GNU setup. So OS X actually came out of this as well. So Apple and OS X. Next is taken over by Apple in 1996 and put Steve Jobs and his Objective-C libraries to work. Now that's the operating system is built out of Objective-C. Redesigned the Mac OS to use Objective-C similar to that of Next Step. Developed a collection of libraries, and this is where Coca comes from. Coca. How do you get Coca out of that? It's like, okay, Coca. Well, they were thinking Java. They were thinking Coca. All of this stuff came out at the same time. I guess they weren't having enough coffee. I don't know. They definitely had cocoa, Coca, coffee, Java, beans. I don't know. Coca was actually the aid for the GUI development. There's probably a history to Coca that I don't know, I'm not familiar with, but this is where the name came from actually. It comes from the libraries that were being used for the GUI. Released the Mac OS X 10, which was radically different from the 9, which was the mock in 2001. This is not going to get into the Intel switch either, but at one point around this time period, I want to say it's in the 10 version, that we switched to be compatible from PowerPC to Intel processors, which was a side note for Apple. Coca API, primarily mostly frequently used frameworks nowadays. So frameworks actually comes out of the concept of the Coca API. It was the window framework, which is why we have to extend framework when we do the GCC, because GCC is the GNU compiler that's working with the framework for Coca. They should have just called it Coca Framework or something. I don't know. NS object here stands for Next Sun, which is the merger from Sun development to expand the language of Objective-C through this company Next Step. It was like an old company for, I don't even know what they made. I want to say hardware, but I'm not sure. Don't quote me on that. You can probably Google it and find out more. Developed by Apple from Next Step and OpenStep, and has a set of predefined classes and types such as NSNumber, NSString, NSDate. We're still using this today, by the way. So now you know what the NS stands for. And I don't have to explain it to you again. And now no one's going to come over here and ask me, can you do this on a Windows system? No. Objective-C is the operating system. It's written in Objective-C. It only supports Objective-C. You can program in C, actually. And because C is a sub-dialect of Objective-C. It's run with the same GNU compiler. So you can do C development on your Mac as well. It includes root classes NSObject. So that's where words like alloc, retain, and release come from. They're actually out of the framework. So now instead of malloc, we have alloc. Instead of we have retain, we have release. So in terms of the dynamic language, almost everything is done at runtime, as we've seen. This is dynamic typing, linking and binding. Also allows for greater flexibility, minimizes RAM and CPU usage actually as well. So to import or include, that is the question. So import head.h. The C include will insert head.h into the code when it has been added before. If it hasn't been added before, which means you can include it in the code, or Objective-C import checks if head.h has been imported beforehand and then includes it. They're both doing the same thing, but the include is the older syntax that's used with C that says put it in there, insert it in, versus use it if we need it, reference it from an import is dynamic. This is static at runtime, at compile time you're including. Both are supported. You can you can import or you can include. They have similar meaning, but they're slightly different in terms of where they come from. The messages, as we've seen, also change. So almost every object manipulates. Manipulation is done by sending objects a message. This is the Smalltalk syntax. So we've seen this already, actually. 2 words with a set of brackets here, the object identifier, the message that's going to be sent to the object, which we've seen. Because of dynamic binding, the message and receivers are joined at runtime. So some say that this is for the dynamic component of the object behavior, because they're blended together, all within the same brackets. I don't know if I buy that, really. So basic syntax structure, the C++ syntax versus the Objective-C syntax, we've seen this already as well, where we take the data type and we put it inside of brackets here. We go minus because it's a method for an instance and not for a class. And we have the function calls here, that integer x, integer y, integer z, and then we have function, object function colon x, y, z. We can actually separate them by commas instead of doing the colons on it. So then we have, I think, see, I'm running low on time too. This is probably a good stopping point, because now what I want to kind of, actually, you know what? Someone remind me I stopped on slide number 54 next time. Because what we're going to do is, this is kind of goes through a couple more examples and then the lecture's kind of over with. And then what I'm going to do is start building assignment number 1 by just writing. So Wednesday, if you bring your computers, we're going to write some code. And then what I'm trying to do is have one what's all PowerPoint, the next one code examples, and then PowerPoint code. So I kind of mix things up a little bit. But I wanted to give you the history of the C and the pointers. So what I want to do on Wednesday is write some pointers in Objective-C, not C++ or C. And we'll use it, same thing with the command line prompts. Write some pointer programs, write some objects, write some messages, and start practicing the little tools, and then get into flow control, iteration, stuff like that. So. But this is a good stopping point for today, and I see the next class waiting at the door. So, questions, comments, or concerns? We're just finishing up using stay. Oh well. All right, well then we're done for today. See you on Wednesday.